1 more minute.
Sure, no rush.
Not immediate. I have to make cuts. Yes. All the best part. Bad jokes will be. So, I guess like any other good thing, we came to the last sort of Clifford section, and Professor Prasad will continue this last section.
Okay, so on behalf of everyone here, I would like to thank the organizers, Mahir and Michelle, who organized this nicely, and let me continue with what I was doing last time. So first of all, I will make 2 remarks. One is that, as I mentioned, that if you are working over local or global fields, you don't get really any new topological groups or adelic groups. But on the other hand, if you are interested in simple groups, since you do have the formalism of B and pair, the TIT system, as I explained last time, you do get many new simple groups which don't arise from reductive groups. For example, if you take a pseudo reductive algebraic group G and assume that it's perfect, so such things are called pseudo semi-simple, and take the subgroup GK plus, that is the group generated by k rational points of unipotent radicals of pseudo parabolic subgroups. So that is a very nice group, and the theory developed by Tietz, where he for the first time formulates B and pairs, the famous paper of his in Annals of Mathematics about abstract and algebraic simple groups. So that theory, actually we did that in the setup of pseudo-reductive groups also. It works, and it gives you that a subgroup of GK plus, which is normalized by GK plus, it actually has to be either finite central or all of GK plus. So GK plus modulo center is a simple group as an abstract group. Okay, so this is my first remark. So you do get many interesting simple groups, but they are all infinite. And the second remark is that if you are interested in Brouillart's theory, which is generally done for reductive groups, and it's very powerful and useful theory if you are doing representations and so on. So you can do these things even in the setup of reductive groups over fields which are Henselian discretely valued, but with residue field which are not perfect. So even if you are interested in just reductive groups, so if you do Brouillart's theory over a bigger class of fields, so usually one does it over with residue field which is finite and so on, to get locally compact groups. But suppose your residue field happens to be an imperfect field, then the Brouillart's group schemes attached to parahoric subgroups, which you will get on the special fibers of such group schemes, may give you groups which have unipotent radical, which you don't see completely, and then you will land into pseudo-reductive groups. And so there is a very distinct possibility of pseudo-reductive groups coming up in Brouwer's theory. And in fact, this is being investigated by several people, but I can name Richard Weiss with Bernhard Mühlher in Germany. So these two people are actually working to see what can one do with Brouwer's theory over these kinds of fields using the theory of pseudo-reductive groups. Okay, so there are developments with applications and so on. Okay, so now let us come back to the structure of pseudo-reductive groups, at least the ones which are pseudo-split, which, for example, over Ks. So the first thing to note, which I began, but then the students came in. So you have G, and you have minimal field of definition for its geometric unipotent radical, so which I have called, so the group G is over K, and capital K is this purely inseparable finite extension over which the unipotent radical gets defined. And then you have map into G prime, which is just the quotient of Gk by the unipotent radical. Okay, so this is of course a reductive group. I have divided out by the full unipotent radical. Now from the universal property of Weyl restriction, since this is a group already defined over a small k, you have a mapping of G into restriction of scalars of capital K over small k of G prime. And this map is of fundamental importance, and standardness roughly means that the group G is obtained from this by maybe changing the Cartan somehow. And Brian explained in what way you can change the Cartan subgroup. So I will not repeat that until it becomes necessary, but note that in general Ig will have kernel, and the kernel will be sitting inside the unipotent radical, because when you go from G to Gk, from when you base change, then the kernel of this map is unipotent radical. So kernel of Ig may not be a smooth group, but it's a group scheme contained in the radical, unipotent radical. And it could be a very nasty group scheme. Okay. That's right. It will, in the bad cases, it will not be subjective, and in fact, you will see when I give you complete structure. Okay. Now there is a situation where you would like, you see, we are going to study Cartan subgroups and so on and make use of them. So you would like this map to be at least injective on Cartan subgroup. So what one does is the following. So you take the kernel of Ig and intersect with any Cartan subgroup you like. And the first thing which we prove is that this is central. So this is always a central subgroup scheme in G. So kernel of Ig, this is not obvious, but kernel of Ig intersected with a Cartan subgroup is a central subgroup. Now you can divide by that, and this is independent of the Cartan subgroup because it's central. Therefore, all Cartan subgroups are conjugate to each other. So this group scheme is actually independent of the Cartan subgroup you choose. So this group scheme, which we denote by script Cg, is a central subgroup. So if this is trivial, so G is said to be of minimal type. G is of minimal type. If Cg, this group scheme is trivial. Of course, this can happen. For example, if my G were this, then Ig will be the identity map, and certainly there is no kernel. So it could happen that this kernel is trivial, or its intersection with the Kartna subgroup you have chosen is trivial. So groups of minimal type. Now any group G gives rise to a group of minimal type. That is, when you divide by CG, which is a central group subgroup scheme, you do get a pseudo reductive group. This is part of our yoga. So the group, quotients, as Brian explained to you, and very simple examples tell you that the quotients may not be pseudo reductive. So one has to be careful. And each time we work with a quotient, we have to prove that it has nice properties. So in any case, this is a pseudo reductive group, and it is of minimal type, namely the corresponding I sub this new group has no CG. Okay, so you get G to script G to 1, and the kernel is a central group. So in other words, given a pseudo reductive group, you always obtain a pseudo reductive group of minimal type, and what you have is a central extension. So if you are going to classify pseudo reductive groups, the first attempt will be to classify them up to central extensions. In other words, just classify groups of minimal type, which, since this they are more closely related to restriction of scalars, you have a better chance. Okay, so that is our goal, to classify pseudo reductive groups up to central extensions. In any case, commutative pseudo reductive groups are hard to understand. So I think it's a good idea to classify them up to central extensions. So that will be our goal. Let me remark that suppose this group happens to be restriction of scalars, for example, of a simply connected semi-simple group, any simply connected semi-simple. Then the claim is that this admits no central extension of the kind we are working with. You see, note that in this central extension, this group actually is highly non-smooth, namely the group G being pseudo reductive, no part of a unipotent radical is seen over the base field K. So in other words, the kernel of the map Ig has no smooth subgroups at all, no non-trivial smooth subgroup connected. So in such situations, we prove that if you start with, for example, a simply connected semi-simple group and take any restriction of the scalar from purely inseparable field, then any central extension by a group which has no smooth connected subgroups has to be trivial. So this is a very interesting result about central extension. So for example, this cannot arise from such a sequence unless G was isomorphic to G. So in other words, sometimes the fact that you have a minimal type group already means that this must be the original group. So there cannot be a minimal type quotient of this kind arising, because this doesn't admit central extensions. Okay, so now let us do some more serious work. I mean, this is a non-trivial theorem, but it's there in the book. Okay, so let us concentrate now on groups of minimal type and look at, so now I am assuming the G of minimal type. And I will also assume, to to give structure that G is pseudo split, which means that it admits a maximal torus which is split. So with T a maximal torus which is split. Okay, so now you take a root group. So suppose you take a root group. So I have root system phi with respect to T, and I take a root A inside phi and I look at the root group. Now you see the torus T by base change to K gives me a torus in GK which under projection goes to G prime. But you know the kernel of the map from GK to G prime is unipotent. So the torus maps isomorphically onto a torus inside G prime and it will be a maximal torus. So Tk, which I will denote by T prime, is a maximal torus. So I can talk of its the root system of G prime with respect to T prime, and the root system of G and G prime could be different, a little different, but in any case I can talk of the root system with respect to T prime, which is nothing but the original torus. Now this contains a unique maximal torus. So see, when you take restriction of scalars of T prime, you get not a torus because we have purely inseparable extension, but it certainly contains a unique maximal torus which I can denote by script T. So inside Rk over K of G prime, I have a torus which is related to, the torus T actually maps isomorphically there. So in any case, you have UA and then you have restriction of scalars of the root group inside G prime. And you see this map is actually group homomorphism from one unipotent group to another unipotent group, and this is equivariant with respect to the action of the tori. I mean the same torus on both sides, because as I explained, T is isomorphic to T prime and the script T becomes isomorphic to T. So you have a group homomorphism here, so an additive map which is equivariant with respect to the torus action. But now you see these groups, because we are working with split situation, these groups have natural vector space structure, vector space structure. These are vector groups, linear, because the torus acts with non-trivial weights on. You see, pardon me? No, U prime A is one dimensional.
Yes, but for the Vera section it's okay.
Yes.
Why is it so for U A?
Because whenever you have a group action on a unipotent group in which there is the trivial weight does not appear,
Okay.
then it has a unique T equivariant vector space structure. Okay, so that's the situation here. You see, only non-zero integral multiples of A are the weights here, and therefore you have vector space structure. And now the map from UA to then additive map will have to be a additive given by an additive polynomial, which means that here the weights appearing here could only be A and PA and so on, where P is the characteristic. Because these are additive polynomials, so they are polynomials made up of with x to the power p and so on. So the weights multiply by p. Now the only group, so suppose PA is a weight here, which means that 1 over p of PA is a weight. Yeah, A is also a weight. You see, first of all, this map at the level of vector spaces is a injective map. The reason is that since it's a map from a vector space to another one, the kernel is actually a smooth group. If you take the largest A, so at the So suppose A does not have a multiple here. So suppose I take A to be a root which is not multipliable. Then for such an A, this map has to be, a map which will have no kernel. It will be a linear map with no kernel. So you have this. So you have a weight here such that 1 over p of that is also a weight. Now the only root system which admit this property is the root system of type Cn. So in Cn, if you take a long root, then half of that is a character in the character group of the torus. And that's the only root system in which this can happen. So which means that the only time you can have a multipliable root is the case when you have characteristic 2, because p has to be 2. Since I said that if pa is a root such that 1 over p of pa is a root, then p has to be 2 and characteristic has to be 2 and the group has to be of the root system has to be type Cn, and the underlying group G prime has to be the symplectic group, not the projective symplectic group, because in the projective symplectic group you see the root system generates the character group. So you cannot divide by half. You cannot multiply by half. So G prime has to be simply connected. So symplectic group, or a form of it. So a form of sp2n simply connected. So the main point is that it's simply connected. So the only time you have the possibility of this root system being non-reduced is the situation when G prime is simply connected type Cn group and characteristic of the base field is 2. And in fact, in this situation you can manufacture pseudo-reductive groups which have non-reduced root system and for which G prime is sp2n. And in fact, this construction is quite hard in the sense that what you do is to construct groups with non-reduced root systems. And these are pseudo split. And you see the first one of this kind was constructed already by Tate, and he for the special field. So the idea is that suppose you have this long root A and you want to find a root system, a group with root system in which half A is also a root. So half A and A both. And what you do is you analyze the possibilities for what U half A can be. So you make a serious analysis of that, and we did that. And what happened? So U half A includes the weight half A and A. These are the two possible weights in the Lie algebra of this group. So this luckily, as we showed, it breaks up at the level of vector groups. So it breaks up into something for half A, plus something for A. So this group in which there are two weights, so it does break up equivariantly with respect to the restriction of a scalar torus into two vector subspace, two additive group subspace pieces, and these pieces actually have some vector space structures under this map. So this map, so I am looking at the image here. So the image here goes into u prime a. So I'm looking, you see this map is injective at the level of rational point. So I'm looking at this map, and the image of UA of course goes isomorphically into that, and we denote it by V prime. And image of this goes into a K square subspace. The reason is that this was a K space, but this is a squaring map. As I explained, you have this additive map is made up of additive polynomials, so half a thing will go by squaring into. So V2 in the image will be a K square subspace, and this will be KK square subspace for some reasons which I will explain to you in a few moments. So your group U half A can be identified with some of two things inside, this, as Briand has already remarked, on right hand side U prime A are one dimensional vector spaces. So I can identify U prime A with the additive group, and so restriction of a scalar at the level of rational points gives me capital K. So these are two subspaces inside capital K, and you can more or less arbitrarily choose these things. The only restriction is that this has to be a K square subspace and this has to be KK square subspace, and they should not intersect, because this at the level of rational points there is no kernel. Any kernel will show up in the unipotent radical, which is absent in the pseudo-reductive group. Okay, so now how do you construct the group? So what you do is, suppose such a group existed, then you will have open Brouillard cell. So you will have the Cartan and the negative roots and positive roots, root groups, and that will give you open Brouillard cell. Now, so you write down what is going to be open Brouillard cell in this group, and you introduce a birational group law there. And then André Weil had this theory of how to extend a birational group law. So that's the way the construction is. So how do you get a birational group law on this Jarsky open cell, which is eventually going to be the open Brouillard cell inside our group to be constructed? So the idea is that you see this open Brouillard cell, which I said, you take negative root groups, Cartan, and positive root groups, and the Cartan is already sitting in the restriction of scalars, because I am constructing a group of minimal type, so the Cartan goes isomorphically onto Cartan here. So my omega is now negative Cartan and positive root groups. Okay. Now the short roots, I take the same root groups as in the symplectic group, namely inside here. Only the long root groups are being changed, because long root groups can be divisible. You can introduce half A and A. So we do that. Now see, you have a map from omega to restriction of scalars of sp2n. Namely, the short root groups will map by identity map onto the short root groups here, and the Cartan will map onto Cartan, and the long root groups, you see, the long root groups were like U half A plus UA, which was identified with V2 plus V prime. So you see, at the level of rational points, the whole thing is going by squaring here and by identity here into SP. So starting with rational points here, I can identify the rational points with rational points of this group, in fact inside. So the rational points here go into the rational points, open cell of the rational point. I mean the rational points of the open cell here. Now I can use product structure here and make sure that if I multiply two things here, then using this map, then the multiplication is given in terms of rational functions. You see, so if I start with 2 points G and H, probably in a smaller Zariski open set, then the product in the image makes sense. And this product I can write as, you know, in terms of some rational functions in coordinates. So that's all done. You know, it's lucky that you get rational functions. So in other words, you get now on a still smaller Zariski open set, you do get product defined by rational functions. So you have you know, rational group law, birational group law, and then use that birational group law to construct a group, and then you prove that this group has all the required properties. You know, nothing is obvious. For example, we do need to use the Chevallier's theorem to say that you actually get an affine group, because see, Andre Weil's construction doesn't give you an affine group. Starting with a birational group law, it constructs a group. So it's not clear that it's affine, it's connected, it has, you know, all the required properties. So, you know, with a good amount of work, we are able to show that, you know, this group is perfect, and therefore it has to be affine, you know, otherwise you will go into an abelian variety. Perfect group cannot map onto an abelian variety, therefore it has to be affine, and then, you know, connectedness and all that is, you know, obtained on the way. So we are able to prove, and in fact, you know, in the first book, this is the longest chapter. In fact, you know, it takes a large amount of work to achieve all this. So let's not go into more detail. Let us now look at groups. Most of them are of this kind, namely those which have reduced root system.
I'm confused by the fact that you're defining the multiplication law by looking just at points.
That's right. So you see, the multiplication law, you see, we have only the crutch of symplectic group. So what we do is, from the, you know, you have short root groups, there is no change, they are the same as for the symplectic group, or restriction of scalars of the symplectic group. And the long root groups now have been split. So you have half A and A. Okay, and there is, by studying what may happen if such a group existed, you know, we studied that, you know, a priori, and we know that there will be a vector space which I call V2, k square vector space, and a k square vector space which I call V prime. And so if such a group existed, then UA must look like direct sum of this V2 and V prime. Now you have a map from V2 plus V prime going into UA, or restriction of scalars of U prime A. So you do have a map from UA to restriction of scalars of U prime A, where U prime A was the group inside SP2N. And this map on half A is just a additive polynomial of degree 2. So because see, this is a torus equivariant map, and the only weight you see is A here. So it means that the half A must become the weight A without leaving any kernel, you know, at the level of rational point. So it must be a squaring map, you know, it's a additive map which raises half A to A, so it must be the squaring map. So we know that on the V2 part it's a squaring map, and on V prime part it's the identity map, because V prime comes from the A weight space, and A weight space goes to A weight space, so it must be a linear map there. So I can assume, because it's a isomorphism, that V prime is identified with the image. Okay, now to multiply two elements, After all, finally the group which I will construct will have the property that this is a group homomorphism. Finally, because G prime is a symplectic group, so in any case Ig is a group homomorphism. So if I multiply two elements here, then the image of those elements multiplies in the right way. Therefore, suppose this map at the level of rational point was known to be injective. So to know what product of two elements is, I take their images and take the product there. Okay, but I have to construct a birational group law. So I must make sure that if I multiply two elements which are in a small Jarsky open set, then the product is actually defined by rational functions. And that we are able to do explicitly. So we first guess what the product should be by using this, and then we show that this product actually is given by rational functions. Yeah, that's some work. And then you get a birational group law, and it satisfies associativity and existence of inverse and so on, because this does. So so you finally get a birational group law, and that birational group law then constructs a group. And it also constructs a homomorphism, because this fellow can also be thought of as a group given by birational group law. So you do get a homomorphism, but it's not clear that G was all affine and G was connected. So all that you need to prove. But in any case, that's all done, and you get a group. This is an interesting problem to construct these groups in some more direct manner. And we didn't try hard enough, but I certainly tried for some time and couldn't find a direct construction of these groups. I mean, it would be nice to avoid birational group law business, because it gives you something which is not so concrete.
So it's some sort of an infinitesimal thickening of the symplectic group.
But it introduces a new root. So I do not know whether it's infinitesimal thickening. No, I think it's more than infinitesimal thickening, because it's introducing half A which was not there. Anyway, this is an interesting problem to think about. Now let us look at groups with reduced root system. Okay, and then the first such group is, of course, a group with root system A1. And here I will have Rk over K of G prime, and G prime has to be a reductive group, in fact semi-simple now, with root system A1. So this has to be either SL2 or PGL2. So the first question is, what are the groups inside Rk over K of G prime where G prime is one of these groups? So you analyze. And in fact, when I was early on this project, when we had more or less characteristic away from two results, then I wrote to Springer, who was still alive at that time, and I asked him whether he, in his book he had some, the second edition of his book, he had some things about pseudo-reductive groups. He calls them something different, K reductive group or something. He has a different term, but we use pseudo-reductive because Titz was using that term. So in any case, he had some partial information in a chapter of his book. So I wrote to him, and he said that he tried to understand type A1 using Jordan algebras. And my impression from that email is that he didn't fully get a list of. So for example, he didn't probably think about minimal type, and he didn't think about problems with central extensions and so on. So he used the Jordan algebra, because he had a book on algebraic groups and Jordan algebra. Is it not? There is a well-known book by him. So in any case, so already for SL2 and PGL2, the theory is interesting. So away from characteristic 2, any such so let's call let's just use instead of G prime, I will use the term L. The reason is that both these groups actually descend to small k. So even though G prime begins its life over capital K, it does have a descent over a small k. In fact, these groups are defined over the prime field. So I will call L to be descent of G prime to small k. So descent of G prime to k as a split group. Okay, so now if characteristic is not equal to 2, then any subgroup which contains SL2, you see, SL2 is there because G contains, as I said last time, a levy. So G contains a levy, and that levy will map onto the SL2 sitting here, SL2 or PGL2. So, you know, instead of saying all the time SL2 or PGL2, I will just say L. L is SL2 or PGL2. So the L inside G, you know, yesterday I mentioned that G contains a levy, and that levy of course will map into the L sitting here. You know, whenever restriction of a scalar is, restriction of a scalar of a group defined over the base field K already contains the original L. Yeah, that's clear from, you know, the properties of Weil restriction. Okay, so we are looking at groups which contain inside Rk over K of Lk, which contain L, you know, the original L. And the answer is that if characteristic K is not equal to 2, then such a group, so let's call such a group H. So H is restriction of scalars of maybe a field inside K for K prime inside K containing K. So this is this you can quickly verify in characteristic other than 2. Now if characteristic is 2, then the situation changes, and the situation changes, namely you have a continuous family of subgroups. So here you see only subfields. Now in characteristic 2, let's assume that my H is large enough to have same minimal field for the unipotent radical as the original group. If it has a smaller field, then you will work with a smaller capital K. Okay, so H with K as minimal field of definition. Okay, let's look only at those subgroups because they are enough. Then there exists a vector subspace V inside K, and this is a KK square vector subspace containing 1. Such that when you take the upper triangular matrices with entries in V, and you take the lower triangular entries with entries in V, and these two groups generate H, and the root groups for H are precisely the upper triangular V and lower triangular V groups. And what is the Kartna here? Kartna here is the Jersky closure of you take V inverse, if you are in SL2, otherwise it's image. So you take Jersky closure of the group generated by these. So Jersky closure of the group generated by. So these groups we will denote by H sub V K over K. So they come from, for a fixed choice of capital K, which is the minimal field of definition, they come from choosing a vector subspace inside K, and there could be infinitely many choices of that. So for any such choice of V as a KK square vector subspace containing 1, you get this group. Okay, now how to construct all pseudo-reductive, pseudo-simple groups which are pseudo-split and which have reduced root system. So suppose you have a reduced root system, and let me draw just for your pleasure one such Bn. Now for each simple root inside G, I will get, so for let's say C is a simple root. So for each simple root, I will get a subgroup GC, which is generated by the root groups U plus minus C, just like in the case of reductive group. And this can be described in terms of centralizer of a torus, a singular torus on which C is trivial and all other simple roots are non-trivial. So you take that such a singular torus and take the centralizer and take the derived group. But a simpler description is, since we already know what root groups are, you just take the plus minus C root groups and take the group generated by that. So you get a pseudo simple subgroup inside G of rank 1. And in fact, under our map IG to R K G prime, and I have fixed a Levy here, so that G prime is actually now has a descent to L. So I have a Levy, I have fixed once and for all. So what happens is that GC then goes into so RK over K of LC. The corresponding SL2 or PGL2. Okay, so the group GC now gives me a vector subspace. Namely, I know what are these groups. Any subgroup of RK over K LC I know. And so this is isomorphic to HV, some field depending on the root, so V sub C. Because as I mentioned, for rank 1, I know what are the subgroups of this. This map may not be surjective as you mentioned. This map may not be surjective, so I look at the image of GC under this map, and that goes into restriction of the scalars of a SL2 or PGL2. And I know these groups. And these arise from vector spaces, as I explained. So these arise, in characteristic 2, and in other characteristic they arise from fields. So these fields are called K sub C, the minimal field of definition for the unipotent radical. Now, so away from characteristic 2, things are nice. You don't get VC, but you actually get the whole field, KC. And if you have characteristic 2, then you might get KK square C vector spaces VC. But in any case, I have then, for each root, I know VC, which in characteristic other than 2 is the field KC. Okay, now you see VC and VC prime are not independent. So suppose you have two conjugative roots. Then the karta here acts on, the whole thing. The karta of GC acts on G, it's inside G, so it acts on G by conjugation. So in particular, it acts on the next root too, the next GC prime. And I know how it acts. because see inside restriction of scalar, the usual, this is a reductive group, and then you are looking at its restriction of scalar. So you know how a co-root acts on other root groups. So for example, if C and C prime are adjacent roots, both long in this picture, then the Kartna here acts by multiplying the root group here by, if the Kartna is parameterized by, GL1, so restriction of GL1, so it acts by x to the power minus 1, because this number 2cc prime by cc, this is minus 1 in this picture. So because of this, you know how Kartna here acts on this. So in particular, VC, and as I said, the Kartna, I know very well what the Kartna was, I wrote down. So you know then that VC multiplies with VC prime and keeps VC prime stable. So in this situation, in this picture, VC prime is contained in VC prime, because the Kartna of GC acts by minus 1. So VC times VC prime is VC prime. On the other hand, the normalizer of the split torus, namely the Weil group, so it takes, it acts transitively on roots of same length. The Weil group acts transitively on roots of same length. And you have Weil group representatives at the level of k rational points in the Levy group already, because the Weil group of Levy is same as the Weil group of G. So using the normalizer of the torus inside L, you already see that C can go into C prime, because they have same length, which means that VC has to be VC prime. So in particular, VC multiplied with VC prime is VC prime, but I also know that VC prime is VC. So in other words, VC is not only a subspace, but it's a subalgebra. But the algebra generated by VC, which I didn't mention, has to be capital K. So you see that if you have two roots adjacent to each other of same length, then the corresponding VC has to be a field, because it's a subalgebra, inside a finite extension. In a finite extension, a subalgebra is a subfield. Okay, so but on the other hand, it could be that your C is here and your C prime is here. Then what do you see? VC multiplies with VC prime and gives you inside VC prime, because the co-root here still acts here by minus 1 power. But on the other, so which means that you have a relationship between VC and VC prime, namely it means that VC is contained in VC prime. So if you have a long root adjacent to a short root, then the short root vector space contains the long root vector space. On the other hand, if I take the Kartna here and see what it does to the root group C, then you see short root. So if you have co-root of the short root, so C prime co-root. So that acts on Kartna by minus 2 power. So you also get that VC multiplied with VC prime to the power minus 2 is contained in VC. But you see, this VC prime is a kk square vector space. So taking minus 2 is same as taking plus 2. So it means that VC prime square is contained in VC. So that actually implies, because when you take the algebra generated by this multiplication action, then it means that Kc prime, which is multiplied with VC, is VC with a square. So you see, this forces VC to be kk square vector space. Okay, in any case, so you have just from the commutation relation, like thing. So how Kartna acts on each root group, you are able to not only say that VCs are vector spaces of certain kind, but the interrelationship between them. Once you have obtained this interrelationship, then from the theorem which I quoted last time, from our book, Appendix C, how to construct inside a given group a subgroup with given root groups. So you use that idea. So now inside this, I want to construct the image of G. You see, we do not know what G is. But whatsoever G is, I have analyzed what are the possibilities for its image. Question is there a group with these required properties? So I am claiming that there is already a GIC. Namely, I use that theorem. For each simple root, I take the corresponding group here with the desired properties for VC, and those desired properties for VC were forced on us by consideration of two adjacent roots, two long, two short, one long, one short. Two adjacent roots are all possible adjacent roots, and I don't have to analyze everything because while group orbit nothing changes. So I have to analyze one long root, one short root which are next to each other, and two long roots if there are two long roots which are adjacent to each other, and if there are two short roots, then two short roots adjacent to each other. So by analyzing three cases, I know all the properties for VC which we should and we can have, and those properties are enough for using the theorem we had yesterday. And you construct a group, and the theorem then tells you that if each of these pieces are pseudo-reductive, then the group you generate is pseudo-reductive and the root groups don't expand. In general what happens is that when you construct groups out of subgroups, then the group may be much bigger than what you would like it to be. Namely, if your original root groups were thin, maybe after generating they have become very thick. You have produced a karta which enlarges the root groups. So our theorem last time told you very clearly that for simple roots nothing changes. The original group which came from simple roots, they stay as the root groups in the new group. So you have therefore constructed completely inside here what should be our desired pseudo-reductive group. And then I am only interested in giving groups up to central extensions. So this map, in fact, since G is minimal type, the image here is isomorphic to G, there is no kernel. And so in some sense I have produced you the group up to central extension. So all pseudo split groups look like this. So let us see some examples. So let's first see characteristic other than 2. So in characteristic other than 2, this construction can so characteristic other than 2, and let's say 3 also. So you will get only restriction of scalars by this construction, because the VCs and VC primes, they all have to be equal to the field K. The conditions which Karta imposes, and you can easily understand, gives you this. Now if P equals 3, then the only time where things can go wrong is when you have unequal length. And the unequal length, if the unequal length, the ratio is 2, then there is no problem, because squaring in a field in characteristic 3, it still is a nice map. So the only time in characteristic 3 there is a problem is when you have unequal length where ratio is 3. So G2. Now inside ordinary G2, You start with a split G2 and just take a basis, and here you take the field to be all of k. I'm sorry, the long root is small. So suppose I take k cube inside k, or if you want to be more general, you just take kk cube. So what you do is long root group you declare to be kk cube. This is a vector space inside k. So think of restriction of scalar. We are inside restriction of scalars. So the additive group is identified with capital K, restriction of scalars. So identify this with K. So inside K, you take the full K for the short root group, and for the long root group, you take kk cube. And so inside the restriction of scalars of G2, you will get from our theorem stated last time, C2.29, you get a subgroup which is a pseudo-split, pseudo-reductive with root system G2 and which is not G2. It has very thick short root group and much thinner long root group. So for example, you might have k cube to be contained in small k. Your k could have been contained in k to the power 1 over 3. So if k cube is contained in small k, then this is nothing but small k. So this root group is just the base field, and the other root group is a much larger extension. So you can have that. Okay, so this takes care of characteristic 3. In characteristic 2, now let us look at type Bn, which I had originally. So in characteristic 2, so suppose I am looking at Bn and n greater than or equal to 3. So Vc has to be kk square, the field itself, and so for all C long, C long root, and suppose this is called B, the short root, and Vb can be any vector space. So you do have a group of type Bn in which the datum is all these root groups are parameterized by kk square, and the short root group can be any vector space inside capital K, big K, which is a kk square vector space containing 1 and generating capital K as an algebra. So you see, you have unlike reductive groups which are split, which are parameterized by discrete datum, namely root system and possibly the center. Here you have continuous datum, namely inside capital K you are allowed to take any vector subspace for the short root group. Okay, now for B2 this picture is not complete, because in case of B2 you don't have two long roots adjacent to each other, which means that suppose I call this root A and this root B, then you will get a genuine vector space VA and VB, and I cannot say that VA is a field, because you don't have two long roots adjacent to each other to play with karta of one against the other. So in other words, for B2 VA could have been a field kk square, but you can be more opportunistic here and you can take any subspace. So which means that the family coming from this construction is not exhaustive for B2. You have more possibilities. Okay, now what is a concrete description of this? So I will finish now. So the concrete description of these groups is you take a quadratic form, regular quadratic form. Now I am describing the split ones. So you take a hyperbolic planes n of them, because I'm looking at Bn, and take a vector subspace, what I call V, inside K, and take the squaring map. So suppose K square is contained in K. Let's consider this situation. Then you take the squaring map on V and usual hyperbolic form, n of them. And you take this quadratic form, V with squaring. You see, V is inside capital K and K square is in small k. So the squaring map on V gives you a degenerate, very degenerate quadratic form. So you take the quadratic space to be n times hyperbolic plane plus this quadratic form. This is a regular quadratic form, though highly degenerate, and the corresponding smooth orthogonal group is a split Bn. And for each group, one would like to know, like in the usual situation, you have universal central extension. So for a pseudo-reductive group, we have a universal tame central extension. So that's again of minimal type. So it doesn't give you all central extensions, but it gives you the analog of what you call the simply connected cover, the simply connected group. So we have this theory of universal tame central extension that works for affine algebraic groups, including pseudo-reductive groups. So we don't construct all central extensions, but we construct this universal one, which has very nice properties. Okay, so I will stop here and thank you again.
Any questions? So in which types do you have these continuous families?
For all types, in characteristic 2 only. For all types, you have the choice. In fact, the one which non-reduced root system, I chose V upper 2 and V prime. You can choose them arbitrarily except for the constants I mentioned. So you have a continuous family, and for all others, Bn, Cn, you have choice of a vector space. So in case of Bn, the vector space has to be coming from short root. In case of Cn, the vector space comes from the long root because that's isolated. And for B2, both long and short roots because they are both isolated. They are not adjacent to a root of same length. Therefore, you have 2 parameter choices. Yeah, so each one. But only when all the roots are of same length, then you have no choice. You don't have choice. For example, type A, and there is no choice. But on the other hand, these are pseudo split ones, but then you have to construct K forms. So of course, so there is the whole theory. So in this short lecture, I couldn't tell you what K forms could be. But yesterday I mentioned.
For the simply laced types.
Yes, they are mostly restriction of scalars.
Are pseudo split.
Yeah. Oh, they are just restriction of scalars.
It's only a finite number.
Yes, correct, precisely. Once you describe capital K, the field extension over which, the unipotent radical is defined, then that tells you completely. Yeah, for simply laced. Up to central extensions and so on.
And those are discrete as well?
Yeah, because as I mentioned in the beginning of this talk, restriction of scalars of a simply connected